artificial neural networks, and also how you can apply, how you can become better as an engineer in A&M. So I would like to make sure that you all give me feedback throughout the session. If you have any questions, you can interrupt me and ask, or I will provide a Q&A session at the end also, where you can ask me any questions. It was 2 weeks back when Naufal, one of your alumni, called me and asked me to take a session on neural networks. So I was thinking, what would I present on neural networks? Then I don't know the audience. I don't know what to say. So what I thought, like, maybe I can go back to my college days. Maybe I can think like, what would I wanted to know when I was in my college doing my BTech that would have helped me become better engineer. So I have prepared this session based on that. So I hope everyone will find it useful. And this is just an introduction, as I said. So you have to keep learning forward to become better at this particular topic. So I have summarized the topics into 4. This is basics of neural networks. Then what are different practical approaches you can use when you create neural networks or applications with neural networks, and how neural networks is applied in embedded systems, and what you need to know as a fresher to excel as an engineer in neural networks. And at the end, I will have a short Q&A session where you can ask questions. So in between, if I ask questions, you can use chat option, or you can unmute your mic and answer me. So I came to know that you have already attended a session on machine learning. So you might know the basics already, but I will just brush up everything and I will go to neural network. So we have prediction and classification, the first one. Then we will talk about what is a neuron in terms of artificial neural networks. And we will talk about different neural networks like CNN and RNN. So before going into neural networks in detail, I would like you to understand the applications of neural networks. One of the important applications is predicting the behavior of a user. For example, you might have used Amazon, right? Have you guys used Amazon or any other shopping websites, online shopping websites? You can answer in the chat itself. There's a chat option there. Maybe you can provide answers there if I ask some questions. That'd be helpful. Okay. Thank you. So you might have seen that Amazon predicting what you're going to buy based on your previous history or based on your username and other details you have provided. So that is based on prediction of what you'll be doing, what you'll be buying on Amazon. So what Amazon does is it will take your data like your name, age, your history, and other data, and it will pass it to a neural network, and it will predict what all products it can recommend it to you. So that is one of the main important applications of neural networks. So there are other applications like we have a prediction of home prices. We can predict stock prices or weather data. We can predict the image, like whether there is a face or not. So you might have seen the Apple has introduced a new face app. So we can unlock your phone using your face. A lot of other mobiles also have introduced that. That is using the image recognition and image classification. Another important application is audio related application like speech recognition or classification of your commands. For example, if you have used Google, OK Google feature in your phone, Android phone, or Siri in your Apple iOS phone, then you might know that you can provide some commands to Siri or Google, then Google will give the particular reply or the reply that you need, or based on the input, it will give you suggestions. What you will say, I don't know. So that is based on the audio recognition and audio classification. Then there is a translation application. So if you go to Google and search on some other sites like Spanish or French or German, there's a feature in Google which will automatically translate that using an engine. So what is running behind is a neural network in there. And there is another very interesting application that is the self-driving cars. So where it will collect all the details of the road and other obstacles nearby using image or radar data. It will use lidar or radar for getting those data. So here we have all these cases we can use neural networks, and we made something possible that was not there before, so 2012 or 2008. So here, what I want to introduce you is the concept of different neural networks. So in prediction tasks like home features or Amazon ads, we can see that it is using some standard networks. It will use regression-based networks to do the prediction task. And in the case of images, image mapping or image recognition or face detection, in those algorithms, we will use convolution networks. So whenever we have a set of filters to be applied on a group of data, then we use convolution networks. And if you see audio and other test data, right, they are all sequential data, meaning when I speak, the data is coming out one by one. So you have to store it somewhere and you have to process it. So you need a memory in the system and you have to do it immediately, and there will be context, meaning when I start a sentence, the end of sentence will depend on my start also. So you need to store the context and you have to analyze that data one by one by giving feedback. So in that case, we use RNN. And in case of image and radar, there will be series of data, but they are kind of a image, meaning they give us data in a multiple parameters, multiple maps. So we use both CNN and RNN, and even prediction also we use. So in that case, we use hybrid networks where you use different techniques like NN or CNN or RNN, and we combine them together to provide the application. So my question to you is, based on the above applications, how many operations does a NN do? So how many operations does a NN do? It can be an image. Okay, they have a question. I have a question here. What type of image in the last column? The last column image can be any image of a pedestrian standing, or can be a lidar image where it will analyze all the light reflections around. So those kind of images, or radar-based images where we have the details of the different, say, you can provide a spectrum of all the obstacles around. So radar does the same, right? Radar kind of detects if there is any reflection from any surface. So based on that, the image is like a radar image or lidar image. That's the image we meant. So my question was, how many operations does the NN do? So to know the answer, we have to just analyze these scenarios. See how future prediction. There is a prediction like we have to analyze the inputs and we have to say what will be the future output, what will be the trend. In the image recognition, we have to say whether the image is of cat or dog. So we basically do a logical classification. And in the audio recognition also, we do a classification where we say this is the input and this is the command or this is the output to be performed. And during the translation, we do a prediction or we do a classification of words. Say Chinese words can be there and we classify each English word and map them into Chinese word. Similarly, for radar or image, we understand obstacles, we classify them, and we predict maybe the path of the vehicle. So basically, all these operations can be combined into just two. It is prediction and it is classification. So in the prediction scenario, we have to predict a value that will be in the continuous range, like price in a stock market, or we had to predict what product we will buy, or predicting what will be the weather tomorrow. So those are predictions, and we will have classification like to detect if your face is on the phone. That is, if you're using a face lock app, then only for your face it should unlock. So whenever an image comes in front of the camera of the phone, it has to detect whether it is your face or not. That is a classification. There can be multiple class also, like so when there is an audio, then we can classify our audios or speech part into different words. The words will be mapped into some numbers and you will predict based on the input audio what is the output number. So everything can be, everything that neural networks normally do can be categorized into two. One is prediction, another one is classification. So what is prediction? The prediction simply is a curve fitting process where you kind of predict the future value based on your current samples. For example, if you have weather data, say you have some data like it was sunny today and there was some cloud around sky, then maybe you can predict based on that tomorrow it will be rain, there will be rain. Or you can predict a stock market price. So today you have $5 worth of stock and it was performing very bad in the past years. Then you can easily predict that maybe tomorrow also it will be doing a bad performance or it will not be going high. So what we usually do is we will have input and output. So in the case of weather data, input will be the current temperature or pressure, and output will be what will be the weather. Say whether it will be what will be the output whether like say sunny or rain or if there is any humidity, those things you can predict. So that will be the output. So what we actually do is we map this input, that is the input weather data, into output climate data. So for that, what we do is we will basically draw a curve which will fit the current data. So you can see there are a lot of orange dots here. Those indicate the current predictions or current data that we have. For weather example, we have the details of the last week's weather, for example. Then those data can be plotted here. That can be the orange dots. And we know what was the temperature on the particular pressure. Then what we can do is we can find out a relation between them using a curve fitting. So you all know the equation of a line, right? So it is y is equal to ms plus b, where m is the slope and b is the intercept. Same thing is used here. So prediction will be y is equal to wx plus b. So we are giving a straight line here, and that depends on our various weights. And there will be a slope here. depending on what is the dy by dx value, and you have intercept here. That will be uh, that is called a bias, and W is a weight. That's why we have W and B instead of M and C. That we will come to know later. So what we do is we basically fit a line so that whenever we have a new value, say what will be the temperature for this pressure, then we can just map it into this line and predict. A better example will be stock prediction, or say prediction of house price. For example, if you have a house price data here, X will be, say, number of rooms in the house, and Y will be the price of the house. So you can have 2 BHK, 3 BHK, or any number of rooms that you will plot in the x-axis, and y-axis you will plot the non-house price. Then we can draw a line which will fit the data, and we can say for this number of rooms, this many number of rooms, what would be the price of my house. So we are predicting because this data was not there earlier. So we are predicting what would be the price for, say, 6 BHK using this line. So how do we do that is using a ML method called regression, where you find out what is the slope and what is the intercept by using set of calculations. So a simple method would be to just draw a line and find out, measure it. Another way would be to just keep on drawing line and figuring out whether you're having a curve or we have a kind of a polynomial line which will fit the data. So whenever we predict data, you can see there is a difference between this line and this data. This data doesn't fit this line. So we can say there is a loss, or there is a difference between the actual value and predicted value. So predicted value is this red dot which I show here, and actual value is this one. So there is a difference in the values. So we calculate loss for that. And to calculate loss, we subtract the value and we just do a square of them. And if you calculate the cumulative loss, we just add up all the differences. Our aim in prediction or in machine learning is to reduce this loss. So to reduce the loss, we use a method called gradient descent, which we will come to later. So in this one, I just want you to know that we plot the line and we predict the values here. That was a case of prediction. So when we predict a house price, or when you predict what the user will buy next time, or when you predict weather, or any kind of predictions you make can be done using a simple linear regression. This method is called linear regression. Then another thing you want to do is you want to do classification. For that, you just have a lot of values and you have to classify. For example, you may have you can have say a lot of voice samples, and you want to know whether the voice sample contains hello or not. So that time you can do classification. So here you want to classify, say, some data which are spread across as a red and green. So you make a line like we do in regression, and you predict the value. So here the only difference is that this line doesn't give a continuous value. Means you don't want, here you want a continuous value like a price of house. Here you don't want continuous value, you just want a discrete value. Means you want to know whether the voice contains hello or not, or you want to know whether the image contains the image of a cat or a dog. So in such cases, you can use classification, and the classifier, what you do is, instead of giving a continuous output, like in the case of prediction, you give discrete output. So in classification, in regression or in Linear regression or prediction, we use the simple equation called y is equal to wx plus b. This will give you a continuous value. To make it into a discrete value, you will use a activation function. So we can use something called sigmoid. So which is a function which will map any value into a number between 0 and 1. So sigmoid is nothing but 1 by 1 plus e raised to minus x. So you can go into deeper details maybe after the presentation. Maybe here just need to suffice that it is sufficient that you know that sigmoid will map continuous values into discrete values 0 and 1. So you can say classification is a result of linear regression plus sigmoid. So you have continuous values and you use a wrapper, which is a sigmoid function, to map it into discrete values to predict whether you will buy a product or not, or whether there will be a rain or not tomorrow. So when you have classification, you will use logistic regression, which is nothing but linear regression plus sigmoid. So I have mentioned that in the slide that there is a difference. There's a loss function here. So when you plot the loss function against the weights or W value, which is the slope of the line in linear regression, what you find is it will be a curve like this. It will be a parabola. So you find the minimum of that parabola to get the W and B, which will fit together. That means this is a loss, this y-axis is loss, and here we have parameter W. Let's assume there is no intercept, that is the line starts at 0, so there is no intercept, B is 0. In that case, you can, if you've got the loss function, which is indicated by J, that will contain a parabola, and you can find out that the loss becomes 0, means our line exactly meets samples. That is what we want. We want to make almost exact prediction. So the loss becomes minimum when you hit the bottom of this parabola. So what we do is we do a descent of gradient. That is, you just find out what is the differential here, what is the slope here, and you subtract the slope. Basically, you just do subtractions again and again, and you come to the minimum. So here you can find out what is the W and B, which will fit the curve, or which will have the minimum loss. So this is called gradient descent, which we use in neural networks a lot. So with that basics, it was this overview of basics. We will go to what is a neuron. So actually we can say that this classification is a mini neural network. That is, it has a function for logistic regression, and you have activation function, which is a sigmoid. So you have the equation for your line, and you have a sigmoid to map the line into discrete value. So a neuron is simply a combination of these two. So our classification model is a mini neuron, we can say. So why we have neural networks? Because these neurons will have a lot of you can handle only a particular parameter, and you don't want to end up getting lower accuracy. So if you see the accuracy of single neural networks, it will be very low. So in order to increase that, what researchers have found that if you increase number of neurons and give the input in parallel, then you can get higher accuracy or higher prediction accuracy or higher classification accuracy. So what we do is we will have inputs. So inputs, when I say why I said input is because we may have multiple values in input. Say for speech, you may have different syllables or different alphabets in a speech. Or in images, you will have various pixels. Each pixel will be transferred as an input. So you may have multiple inputs in the input layer, and you will pass that into different neurons. So you will have a layer of neurons, which we call hidden layer, and you will do the same logistic regression here and pass it to the output layer. So you can have multiple layers in the output also. If you have multiple classification, like if you want to classify into various groups, then you have multiple layers in the output also. But normally we will have a simple class for binary classification or simple 1-0 classification. We will have single output layer. Or prediction also we will have single output layer. So based on the activation, it will converge, and by modifying the parameters, you can predict what is the output or what is the exact value of, say, what is the weather tomorrow, or what is the product you are going to buy in the future. Right? What we do is we have a reduce the loss function, right? So what we do is we will first find out what is the output y, and then we will try to reduce the loss function. So when you find out y, you know what is the loss. Maybe I had to, before that I had to tell about different data sets. So we will have some data of the previous input, like for weather, yesterday what was the weather, and maybe 2 days back what was weather. So those data are there. Those are labeled data which we already have. So we will try to fit this layer with those data. That is, we'll find out what this layer will perform, how this layer will perform when we have our trained data, or whatever data we have, which is kind of already known to us. Meaning, for a house, for a 4 BHK house, 4-room house, how much is the price? If you already know that, we will pass it here. So what we can do is we can find out what is the loss here by subtracting, or simply by doing some using some equations, we can find the loss. Then what we do is we will try to do adjusting of weights. So you have weights, right? Weight meaning the slope and intercept, W and B. Then you find out the weight. So what you do is you pass it back and you figure out what is the weight where losses very less.
So we have a question in the chat section. Okay.
Okay. So activation function. Activation function is named because it is used to activate the subsequent layers. So here, the activation function is, say, for example, in our single neuron, it was a sigmoid for classification. And the activation function will basically give this input, and it will map whatever weight you calculated or whatever prediction you calculated, it will map into linear space 0 or 1. So why it is called activation? Because it is acting as a input to the subsequent layer. So here, for a single neuron which does classification, activation function is a simple sigmoid function. But in case of prediction, activation function will be 1, just a 1. And in case of other networks, there may be a softmax function, or there may be a tanh function, or there will be different functions. This is basically it will just map your input and activate the subsequent layer using the input. So your input, you have to do a curve fitting, and the curve fitted output will be mapped to the subsequent layer. That's what activation does, basically. Is it a CNN? It can be a CNN, but for CNN, you need to perform convolution. So we will come to that in subsequent slides. So here I have given a lot of various activation functions. So you have sigmoid, which is from 0 to 1, and tanh, which is -1 to 1. The same as sigmoid, just you remove the bias. There's a bias here, 0.5. That will cause a lot of problems, because if you average, there is a RMS value will be around 0.5. So you'll take a lot of time to converse. So what you do is you just move this towards zero origin so that the mean will be zero. That will make the gradient descent faster. And you have ReLU function, which is almost similar to this sigmoid, but it is linear. So it doesn't have this curvature and all. So it is easier to compute. And this has actually improved, this ReLU function has helped to improve the computational efficiency of neural networks. And there's a leaky ReLU to kind of simulate sigmoid function. So ReLU plus ReLU with the negative values simulator for sigmoid. That is leaky ReLU. Yeah. So you have various layers in neural network and you have various units here. And each unit will perform two tasks. One is the basic regression and second is the activation. So based on the activation, you can have 0 or 1 or prediction. So if you have a sigmoid here, you will get a binary classification. Or if you have a softmax here, you will get multi-classification. If you have a 1 here, then you get prediction. So like that, depending on activation function, you can change the task performed by the neural network. So you basically repeat a single neuron so that you get more accuracy or more detailed learning. You have more neurons, meaning you have more features extracted and you have more learning. That's the idea. Okay. So coming to CNN. So we can do image classification using this network also. Means we can pass all the pixel values as input to this neural network, and we can use a sigmoid function or tanh function to provide a binary value, and the output ladder also you can use a sigmoid to give a value, say 0 or 1, where 1 indicates a cat and 0 indicate there is no cat in the image. But if you see image processing, you can find out that there is a better method of using filters. So filters meaning you have pixels in the image, right? So those pixels can be multiplied with some values to understand what is in the pixel. Suppose you take this portion of image. Then there's a line here. To detect that, we can just multiply this portion of image with another small image, which will tell whether there is a line or not. So the other image will contain values like 0 here, or the thing 0, and here there's a 1. So whenever there is a weight, it will get multiplied, and you know that there's a gradient of, there's change of pixels, so there's change of color basically. So those filtering is already there in image processing. So CNN basically what does is it will find out features of the image using the filters. So we call the filtering process as convolution because you are multiplying the image pixels with another filter. So you call it as convolution. So convolutional neural networks will find out features of the image using various filter parameters. Okay. So I thought there were some questions. You can ask in the chat if you have any questions. So what we do is in convolutional networks, we will find out various pixel parameters or various image features using filters, and the filter coefficients we will try to figure out. That's what we do in CNN. So since you are using segments of image, you will have to do some extra layers like polling layers or flattening layers so that you don't want to make the entire thing complex. Meaning, we will have a segment of image, then you had to slide those filters over the entire image to get features. So if you have a small filter here, you may have to slide it like in the horizontal direction to get different features. And this will be a complex process. So to make it better or make it simpler, we use various layers. like pooling or dense layers to make the process faster. So since we have filters here, since we have masks here, you can find out different features, like you have an object here, or we have a face. That is what is done in your face app mostly. So it will use the CNN in the cloud, and will figure out whether there is any face or not. So it is basically a neural network only, but you will have some more filter layers, or different multiple dense layers to accept various inputs, like the image features, and to find out various segments. And also, like I said, there will be flattening layers, so pooling layers to reduce the complexity. So these are the applications of CNN. One is image classification, then object detection, and transferring image, means creating a new image from the existing image. That is also an application of CNN. Then there's RNN. So RNN is basically used in all the audio processing. So you may be using Siri or OK Google voice assistants, and all. What they do is they basically operate on your sequential audio data, and they store the data internally and try to predict what are you trying to say. So the applications are very huge for RNN. So you have speech recognition, you have NLP, means you have sentiment classification, you have DNA sequence analysis, translation, then video frame activity detection, and you have name image recognition, like if you want to understand the names in a sentence, so you want to provide Google search results, they will all be using RNN. So we have a stream of data like text or audio, then you want to process something, use RNN. So RNN is simply neural network with a feedback. So feedback meaning whenever you get data, you will find out the output. Say you get a word, you try to figure out what the word is, and you give it as an input to the next line. So this kind of figuring out, means this kind of storing the previous input, makes RNN predict the sequential model or sequence of data. So unlike in here, where we only do it at the end, here each layer, each neuron will have a, or each layer will have a prediction, which will be given as a feedback, so that other layer know the context. Say if you have a sentence, then you can't just take a one word and predict what the sentence is about, what the sentiment is. So you need an entire word. So you may want to do a sequential prediction. So for that, we give feedbacks using the RNN. There are different methods like GRU or LSTM to find out, or to basically memorize or forget words, or to gate various layers. So we have many various methods like GRU and LSTM to predict our audio or text. What is meant by our audio or text means it will identify our audio or text, and it will try to figure out or map it to a dictionary, or it will map it to a task to be done. Say if you say Google to give a phone call, then it has to understand that who the phone call has to be given, all those things. So it is done using RNN. So this, okay. So we have learned about various networks. It's easy to construct networks, but the problem is that we will need a lot of time to train, and the problem will be like it will overfit. Overfitting meaning it will predict very well for testing data, but in the real life it will predict very bad. For example, will be a line which will cover all these points in regression. So if you draw a line which meets all the points, that will be a very complex model, but it predicts very well. But for the actual data, it won't be performing well. So that is called overfitting. So you want to avoid such kind of issues. So we have a lot of optimization techniques like regularization, which will avoid overfitting by adding weights, adding some Euclidean weights to the model. And there's a dropping method. So you want to drop some of the layers, some of the neurons. Say you can remove some this neuron and try how this behaves. So that is a dropping method. Then mini batch training design means you take input as batches and you will have a batch-wise training, and you can easily converge using mini batch gradient descent. Then another method of making it faster is using RMS propagation. So instead of using this slower gradient descent convergence, we can use some methods like exponential prediction to make it faster. Then there are a lot of hyperparameters, including this WB and narrow stop values, then how many drops to be done. All those things will become parameters and we will basically tune it. We find out various methods for the same. We will come to that at the, yeah. So these are the theoretical approaches for optimizing features, optimizing neural network in general. This will give us faster prediction, as well as it will avoid problems with overfitting or high variance and bias. Bias meaning you are actually underfitting the data, and variance meaning you are predicting it wrongly on the actual data. Overfitting. So there are a lot of practical approaches that you can do while you're designing networks. While you're designing networks, you can use different methods like ensembling and all. So basically, when you create a network from scratch, right? So you need to collect a lot of data. So collecting data means it is very difficult, right, to get images of, say, human faces. So you have to use different already collected data from the internet. You can use data sets from Kaggle, for example. So we usually use data from Kaggle or some of the universities who already have data. And another method is called ensembling, where you will create different networks and you kind of vote to figure out which one performs better. So instead of creating a single network to solve your problem, you will create multiple networks, say with random weights, random initialization. Then you kind of vote against those samples or against those models. Then another one is data augmentation. So you need a lot of data, but you have only a few data. So what we can do is we can just uh, modify the data in such a way that it will become wrong data, or meaning it will become a negative sample, or it will become a different sample. So for example, in case of image, you can do mirroring of image, or you can do a cropping, or we can just zoom the image, and also those will become different data sets for you. So you improve the accuracy because you have more data to train. Then transfer learning. That is the method we usually use. That is, you take a model from GitHub, which has already been trained by somebody, and you just add your features at the last level. That is a very easier method that is followed by um, most of them are engineers. And there's a hybrid method. So you use different neural networks together to create your application. There was a contest by Netflix in 2008, around 2008. So uh, they gave around a $1 million cash prize for those who came up with a very good model for their video prediction. So what the winning team uses a hybrid method that perform way better than other linear methods. Hybrid methods will provide you better alternatives. It's not a hard and fast rule, but still you should always try comparing methods to get better accuracy. So we basically use neural networks in various systems. It can be net computing. So if you have a Google, OK Google kind of application, it is actually working on cloud. So you're not actually doing it on the machine. So that is called edge computing, meaning you are running it on the cloud. Then you have robotics application like in the drone sender, you want to recognize the path of travel, or you want to identify obstacles. So you use CNNs, and we actually use OpenCV for those applications. And voice assistants. So we use LSTM or GRE-based networks for voice recognition. So especially in embedded systems, if you want the model to work on the embedded system, so you have to provide a lot of tuning and performance analysis, because embedded systems will have basically very low capabilities, like power will be low and memory will be very low. So power consumption will be milliwatts, and memory will be in KBs. So you want to run it on that. So you optimize the algorithms for that. Yeah. So okay. Now the last section. So this is the overview. It is a vast topic. You might have already understood by from the slides, I think. So you need to learn ML and neural networks, and a lot of new research is coming up. So it should be updated with that. That is one thing. So we can, if you are a beginner, you can start learning by using various online courses or certifications. One of the interesting will be Coursera DNN. So it is run by a very good professor who has experience in ML. And you want to read a lot of research papers from Facebook or Google, or from archive, a lot of um, databases in internet where you get research papers. So you might want to read those papers to get updated information on the developments in ML. Then podcast is another way. You can listen to podcasts where you can listen to the interviews of various ML pioneers. Then one of the important things that I would suggest is to understand the business. So you may be studying right now, but if you know the business value of what you're learning, then it will be very beneficial for you. So that was something I was missing when I was learning. So I would suggest that you uh, understand what is the business model that companies follow. Maybe you want to work in a company as an engineer, or you may want to start off your own, or whatever it is. It's very important to understand the business model. So maybe when you are getting paid, how is the money coming out? Who is the end user? What is the user's needs? So how do you solve the solution? That will make your position better if you understand the underlying business models. So you can do that using Business Insight websites, or using various online articles, books, and all. So you understand the business model and finances. This will help you pretty much. Then I will not tell you, you need to develop ML applications to become a better ML engineer. Unless you do hands-on on this, you are never going to be an expert. So please find time to um, try open source ML, or the problems that you find in Kaggle or other websites. So I have given the websites here. Kaggle is a very important site where you can find a lot of competition. So you can find a lot of free codes and data which you can use to learn and practice ML. And another thing is a collab. There's a collab by Google, which is free uh, Python notebook. So if you know Python, you can try out various libraries like PyTorch or TensorFlow or Keras in this one. And maybe you can build from scratch if you require that, or you can import some notebooks and try. So when I was doing ML back in 2017, the main constraint was I didn't have a system. So now it's not a problem. You have a lot of resources. Google is giving free resources to you online, so you can just go there and try out your ML algorithms. Then you can learn a lot from Twitter and LinkedIn. So they provide a lot of insights there. So you can use various hashtags like machine learning or deep learning to find out the latest news, etc. And maybe you can have communities where you can create a community in your college itself, or you can be part of other communities nearby, or online communities like Jovian, where they discuss about various ML development and they help each other on how to become a better uh, ML engineer, or how to become a better engineer who creates artificial networks. Yeah, that's it from my side. So you can ask questions. And PyTorch and TensorFlow, which is better? Okay, I personally prefer PyTorch. It is just a personal preference only. Both has its own tools, and PyTorch is kind of easier, I think, to begin with. TensorFlow has a lot of resources, and it is done by Google, so it is more kind of powerful, I think, in my opinion. Shall I? Okay. Polylars are counted to. So um, we can use various methods for that. Actually, okay. So what maybe ArcNet or what Linet does is they will provide maybe a dense layer in between, and maybe the fully connected layer will be at the end, and you provide the flattening, and you give the output. So there will be a CNN. First, there will be a. I don't have a figure here. So it depends on the application actually. So pulling layers will be first connected to a maybe say for Ascent, I think it will be like a you will have the pulling layers first, then CNN, then convolution layers, then you have dense layers, then maybe flattening layers, and you have fully connected layers together. So I think that's what you meant, I think, right? Padding can be done in different ways. So you can have simple ways adding zeros. So padding is done basically to avoid the edges or avoid the issue where you have edges in the image. So you may not have enough pixels when you slide the window. Let me go there. When you slide a window over the image, you may not have enough pixel at the edges. So what you do is you add some zeros to account for that. So it can be simple zeros or it can be based on some algorithms like you just mirror it, or you can have a gray shade. Rough techniques are there. Which metrics? Okay, which of the networks would be advantageous for real-time application? Which of the networks? Okay, for real-time applications, we can use say real-time, meaning you have sequence of data, so you want to process it at the same time. So in that case, you can use RNN. For example, if you have a voice data, depends on application, meaning if you have voice data, then you can use a symbol classifier or symbol classifier based on RNN that will give you, let's say, recognize speech, or you can have a real time, maybe say if it is a drone application, then you can have a face recognition system that will use CNN in behind, and that can give you better. Okay, that depends on the data. Yeah, that depends on data. So if it is multiple layers of data, you have kind of you want to apply a lot of filters on it, then you use CNN. Means basically, if it is image, use CNN. If it is audio based, use RNN or just use RNN. It's very simple way to say it. Yeah. Okay. Okay. In this way, how padding can be done? Okay, I didn't get the question. Okay, so polling is done to remove the lot of filtering we do, right? So what the polling is done to remove a lot of kind of features which will be unwanted or which will be which not make sense in the image. So I don't know. Padding is done. Okay, depends. Okay, this in this way, how can padding be done? I didn't get the question. Or maybe you can unmute and ask. Okay. Okay. I still didn't get the question. Okay. So it depends on the application. Maybe if you're using some, so do you want to use drugs? Possible to use same photo. Okay, can be asked. So if you want to create a custom network, then maybe you can use pooling um, after the padding is done, or maybe you can just remove the features. Suppose you want to do convolution, maybe you can um, do padding before it, or after that. Depends on your kind of application, how you want it. Basically, what they do is you do the polling and you kind of remove all the unwanted features after you do the convolution. The RGB image, yes, can do that. Is feedback mechanism necessary for deep learning neural networks? Is it possible to use CNN for automatic learning engines? Feedback mechanism is not necessary unless you want to provide some, unless you want to know the state of the current learning. If you want sequential data, you need feedback, otherwise RNN is not necessary. Learning engines. So what do you mean by automatic learning engines? Okay, so CNN is, yes, we can use. Actually, we use CNN and RNN so that we reduce the number of um, complexity in the RNN. Means CNN can kind of convolve all those audio features together. Then you apply a GRU to kind of find out whether the voice was detected or not. So in that way, you make the model simpler. So I was working on a audio engine. So what we do is we provide a CNN first to convolve the audio samples. Then after that we use GRU layer, which will kind of reduce that complexity of our application. So we want to use it in embedded systems. So we didn't want a lot of complexity there. Thank you, sir. So you can contact me in Twitter or LinkedIn if you have any further questions. That's it from my side. Thank you. If you have any questions, you can ask it now. Or, yeah, sure. This is my contact. You can. Yeah, you can connect with me in Twitter and LinkedIn.
Thank you, Gilson. Yeah, over to you, Anha.
I thank Mr. Gilson Varghese for the wonderful session and Mr. Abdul Sundaresan, Chairman of GCW Alumni Association Bangalore Chapter, and Shabir Sir for giving us the opportunity to host the event. Last but not the least, I would like to thank all who participated in the event to make it a success. Thank you.
Thank you, guys.